Okay, let us start.
Okay. So let me share my whiteboard. Okay, you see my whiteboard now?
Yes.
Okay. So so I'm going to talk about embedding. Oh, so by the way, so make sure you ask questions. If you have questions, please interrupt me and ask questions. I'm going to talk about embedding of simplicial complexes into double dimension. So imagine we have K, which is a simplicial complex, and I say that, so let's it be d-dimensional. Then I say that K embeds into double dimension if there is a continuous injective map into R to the 2D, right? So so the map is on the underlying space, but I also show the underlying space by K. So if there is a way of mapping the complex injectively into R with twice its dimension, I say that then that K embeds into double dimension. So just for notation.
You mean topological embedding or piecewise linear?
Here, for this talk, we can think topological embedding.
Mhm.
So for instance, for d equals 1, K will be a graph, and then embedding into double dimension will be the same as planarity. Okay, so the question now that I want to answer somehow partly is that if we are given two complexes K and L, and what can we say about the embeddability of the join of those two complexes into double dimension based on the embeddability of the factors or based on the other properties of the factors. So we want to have a criteria that tells us, I mean, you can embed the join if the factors are blah, blah, blah. So this is the question. And so as you know, the join of two complexes is another simplicial complex, which you just form by taking one simplex from K and one simplex from L, and then computing the join of them. And you do this for all the pairs of simplices, and then the resulting space is a simplicial complex, which is the join complex. Now there are some results in partial results for this problem. For instance, if K and L are some special complexes, which I talk about later, or if one of these K and L is a 3-point set, so this so shows a 3-point set, then in his paper, Sergey and his colleague, so they showed that this, for instance, if L does not embed in double dimension, then the join of it with 3-point set does not embed in double dimension. And I also showed this independently by some techniques which are similar to what I'm going to say today. And there's also another proof that we worked out with Arkady Skopenko. The other cases are when the Van Kampen abstraction of K and L are non-zero modulo 2, which I talk about in details later. So may I talk about the definition of the abstractions? But, so they are known in some cases, but not a general result. Okay, so we want to study this problem. And actually, to attack this problem, it's useful to think that we want to show that the join will not be embeddable into double dimension when the factors are not embeddable into double dimension. So let's assume we want to prove such a statement. Okay. So as we know, so for the case of graphs, which is d equals 1, we have these two subgraphs. Sorry, we have these two graphs. So this is K5 and this is K33. And we know that by Krotowski's theorem, so a graph is non-planar if and only if it has some subgraph which is homeomorphic to one of these two. So we can think of these subcomplexes as some kind of an abstraction to embeddability of a graph. So abstractions in general mean that some object that prevents, so if we look for that object and that prevents the embedding to exist, right? So we can think of these two subgraphs as abstractions for embedding into a double dimension for d equals 1. So this is not very old. And for d greater than 1, actually there are other abstractions which they are defined based on some other spaces connected to the original complex, which are called dilated join and dilated product. And here also the abstractions for embedding into double dimension of general dimension is a classical topic. And okay, now to talk about these abstractions in higher dimensions, I will define these two spaces. So perhaps everyone knows here, so I just go to them quickly. So the dilated join is, so you take the, so I show it like this, is the join of K with itself, but when you are forming the join of K with itself, you only make the joins of those simplices which are vertex disjoint. Okay, so you put those joins of those pairs into your join complex, and this gives you the dilated join. And for the dilated product, so this is a simplicial complex.
To make sure, so you are taking the union of the joints of these joint simplexes, pairwise disjoint simplexes, right?
Yeah, yes. So therefore, this will be a simplicial complex, right? But dilated product is not a simplicial complex. So dilated product you form by taking the product of disjoint, vertex disjoint simplices. So we denote it by this symbol. This is a, so each cell complex for each cell is just a product of two simplices. And these are actually complex. This is a simplicial complex, and this is a cell complex. So there is, okay.
So again, you're taking products of pairwise disjoint simplexes, right?
Yes. So when I use this symbol, I take the product of simplices. But we can also define, so let me write it here. For a general space X and Y, we can define the join, right? This is famous. So the join is the the union of all line segments that we can form between these two spaces. And let's say, okay, so this is,
So you probably assume that X and Y are embedded into some Euclidean spaces, for example, right?
yes, we can do that. So, or we can take this class to be some kind of formal sum, or as you said, we can think of X and Y to be embedded into two, let's say, a skew disjoint and skew subspaces in some very high dimensional Euclidean space, and then this plus, actually we can take it to be the real summation of these vectors. And there's also other definitions of the join. Okay, T here is 0. And also we can take for an arbitrary space, sorry, can take the dilated join to be the join of X with itself minus the subspace, which is the halfway through, I mean, it's half X plus half X. So you remove this kind of a diagonal of the join from it, it gives you the dilated join.
Okay, but this is different from what you had before. Now this is, that was a simplicial deleted join, right? And
Exactly.
Just deleted.
Exactly. Yeah, so when I apply this notation to a general space, I mean this definition, but when I apply it to a Simplicial complex, I mean a Simplicial complex. But I don't use this much. So this one I use only for the Euclidean space. So these are different. You're right. So these are different. So do you see something here? So it shows something here?
Yes, I see it.
Okay, so let me fix this one. Okay, I think it should be better now. Okay, now let's find some other embeddings, and this time in the dilated join. So let's assume we have the embedding into double dimension. So these things are standard, I'm going to say now. And this embedding allows us to define a function, let's say f star, from the dilated join of K, again, embedded into the dilated join of R to the 2D.
So here R to D is triangulated in some way, and you are taking simplicial deleted join.
I'm taking the definition I just said with the X.
Okay, but K was a simplicial complex.
Yes.
Okay, so the simplicial deleted join is smaller than the non-simplicial, so it has the embedding.
Yes. And so it's okay. So, and this actually is simply you just imagine doing the skew subspaces. So you imagine the image into these skew subspaces and then forming the join of the image of F. So the formula for it would be, so let's say of X. And because this is embedding, we will never touch the diagonal here. And so this is well defined. And by the way, these deleted joins and deleted join and deleted product, they have this involution, and they have an action of Z2 on them, which is famous. It exchanges the factors. And so let's see. So there's this T. So for instance, and so this defines an action of Z2.
Probably this formula is for a deleted product, and for a deleted join, there is a similar formula.
Yes, sorry. Okay, so this is for deleted product. Also, I denote it by K. For deleted join, and then say that okay. So I write this T as an S. I think we should take this.
So because the diagonals are removed, these actions are free.
Exactly. Thank you. And you see here, we can take another also. There's also another action on the deleted join, which we can also exchange these coefficients. Okay. So these are the definitions. And now if such a map exists, oh, by the way, so we know that there is some map of this space, the deleted join of R2D. So there's an equivariant map into the 2D dimensional sphere with the antipodal action on it. So the spheres always have the antipodal action on them. So I won't explain this, but this is known. And therefore, now imagine if there is some...
Maybe 2D minus 1, no? Not?
No,
Yes.
no, the deleted join is 2D.
Okay.
Minus 1. So this is a equivariant homotopy equivalence. Actually, I think that this deleted join deformation retracts equivariantly onto a copy, onto such a sphere.
Okay, possibly, yes, okay. And yes, now imagine if inside this deleted joint is an antipodal sphere of dimension 2D plus 1. So observe that, so dimension of this object is 2D plus 1. So if there is an antipodal sphere of dimension 2D plus 1, I'm sorry, if there is a Z2 sphere here, then the Borsuk-Ulam theorem tells us that this map cannot exist. So for instance, if there is some kind of, let's say sigma, where sigma is homeomorphic, equivalently homeomorphic to the s to the plus 1, then the Borsuk-Ulam theorem tells us that the F star cannot exist, and therefore these objects, like these spheres, they can work as an abstraction. And for instance, if the dilated joint itself is an sphere, and that actually happens. And let's see now what use we can make out of this abstraction. And if we look at K5, K5 is the one skeleton of the simplex with 5 vertices, right? So I denote by delta 5 the simplex with 5 vertices, so it's a 4 simplex. And the one skeleton of it is K5. Now, if you want to find two complexes that do not embed into R4, we can try to extend this construction. So let's take the 2 skeleton of a simplex with 6 vertices. So this guy actually embeds in R to the 4. And let's take the 2 skeleton of a simplex with 7 vertices. And it is actually, if you look at now at the dilated joint of this, so let's our K be this, then the dilated joint, this is actually a sphere, so it's of dimension 5. So I think this was shown by Flores. I'm not sure, but I think this observation is by Flores. And
you mean so, Z mod 2, right?
Thank you. And it is also the exact homeomorphism is also written in Grunbaum's paper. And therefore, these objects, I mean, this complex does not embed into R2, say R4. Okay, so these objects, therefore, I mean, the equivalent spheres inside these dilated joints, they work as abstractions.
You can say, sorry, you can say the same for the graph A5. Its deleted join, Simplicial deleted join is homeomorphic to S3. And because of this, K5 does not embed in the plane.
Yes, that's true. And there is something nice about this, about this special dilated join that is very helpful for us, and I will talk about it later. But before that, let's go into another kind of abstraction, which are the chromological abstractions to embedding. So these are traditionally defined in the dilated product instead of the dilated joint. And so another proof that the same complex here, the 2 skeleton of simplex with 7 vertices does not embed into R4, is given by Van Kampen using an approach which now we can explain it as follows. So first, let me define this abstraction in a very general way. Let's take S infinity with the antipodal action, and let's take the deleted product of our complex and take any map you want from this Z2 space into the other Z2 space, let's say G. So this is Z2 map. And this G exists always. So you can just start embedding any Z2 complex into S infinity by embedding the vertices and then edges, etc. And so there is some G, and because it's equivariant and the actions, okay, so because it's equivariant, we can take the quotient over T, sorry, quotient by this action, and this gives us some map into the infinite dimensional projective space. And so the cohomology of RP infinity is, so is what I write here, H star of so when I don't write coefficient, so I mean integer coefficients. So there is some Z in dimension 0, and then there is 0 dimension 1, and then after that you have Z2, and sorry, for dimension 3 you have, and so like this. So in even dimensions you have a Z2, and in odd dimensions you are 0. And now let's denote the generator here. So the single element of this Z2 by, let's say, alpha 2, and this one by alpha 4. And let's VK be, so this is the defined component abstraction of K. I mean, just define it to be the image under the G star of alpha of dimension, which is the dimensional complex. Just tricky.
Maybe G tilde star.
Yes. Okay. So on the other hand, similar to what we did for the deleted join, whenever there is embedding, then we have a map, let's say F cross, from the deleted product. Oops, into the deleted product of let's say deleted product of R to the 2D, which is yeah, we know what it is, right? So the R to the 4D minus the diagonal. So the diagonal is this. So I need to erase this one here. Okay, now we know that this space again is the deformation retracts equivalently into S to the 2D minus 1. And it tells us that if you want, there is a map of it into S infinity, which actually goes up to S to the 2D minus 1. And therefore, the existence of this F means that the Van Kamper abstraction has to be 0. So this is the chromological abstraction. And so now I want to say why the abstraction in the deleted join is better, at least for us. And the reason for that is, if we now look at it, is the deleted join formula. Here, and the deleted join formula, it tells you that if you take the join of two complexes, and if you want to compute the deleted join, this is actually Z2 homeomorphic to the join of deleted joins. So the deleted join of joins is join of deleted joins. And now remember the two spheres that exist in that might exist in K and L and are abstractions to embeddability. Then it's immediate then if, because of this formula, if those the spheres, Z2 spheres. So if these Z2 spheres exist in K and L, there will be a Z2 sphere in the join, the deleted join of the join also. So if you have some Z2 sphere in here and Z2 sphere in here, then the join of those two Z2 spheres will be another abstraction to embedding. So this formula already tells you that, for instance, the join of delta, say what, 7, let's say K5, this does not embed into this is 2 of dimension 8. Because there exists Z2 sphere in it. And this is actually the theorem, is a theorem which is proved in a paper by Grunbaum.
Sorry, not R7.
No, it's a double dimension, so it should be even.
But what is a double dimension? Because
It's twice the dimension of this object.
Okay. Sorry. Can you write the name? Who proved?
So I think this. I mean, the proof is as I say right now, but this is in the paper by Grunbaum. And it's called Van Kampen-Flores-Grunbaum theorem. that you can form the joins of these, and it's also in the book by Matuszek using the Borsuk-Ulam theorem. It's in there also. It's an exercise. So using this deleted join is really easy to prove. Okay, so now we want to have a similar look, and it's conceivable that instead of actually looking at exactly Z2 spheres, we can look at some subcomplexes that are similar to Z2 spheres, but they are not exactly homeomorphic to Z2 spheres. And it should be possible that there are subcomplexes in the deleted join which they can work as abstractions in a more general situation, and they are not necessarily Z2 spheres. And those kinds of abstractions, they actually exist in for the deleted product. To see that, let's say we compute the Van Kampen abstraction, as I said, in terms of with Z2 coefficients. So let's say V2 of K be the Van Kampen abstraction with Z2 coefficients. Then we know that the with Z2 coefficients, so there's duality between homology and cohomology, and this class that you have if it's non-trivial, then there is some cycle, there's some mode 2 cycle, such that if you have a representative let's say phi of this class, then and you compute it on this cycle, it will give you 1. So it's the dual of it. So you take a class of the dual homology class to this cohomology class. And because here is a cycle, so whenever you have a cohomology class which on a cycle is 1, that shows you that this cohomology class is non-trivial. But in Z2 coefficients, a cycle is nothing but is a subcomplex. Is a bunch of here is a bunch of 2D cells. And so it tells you that in general, also for when the mode 2 abstraction is not 0, we can find subcomplexes that they actually look like they are abstractions to embeddability. And why they're abstractions? Because if this is true, then we know that you don't need the rest of the space, because if you look at this cycle, this cycle Z itself, wherever this cycle, something like this, I mean, this cycle Z exists in the deleted product, then that complex will be non-embeddable. I mean, it does not depend on so I mean that this C is a subcomplex of the deleted product, and you can find in the deleted product of other spaces objects which are homeomorphic to this complex. If you find that, then those complexes will be also non-embeddable. That's because this phi, you can think of it as also as another definition of the Van Kampen abstraction is is given by the intersections, right? So this relation that a representative of the Van Kampen class is one on this cycle means that regardless of how you draw your complex, there will be odd number of intersections between the simplicities that appear in this cycle.
Sorry, I think in the top line you should have quotient by involution, right?
Yeah, that's true. Sorry.
So this cycle Z lives in the quotient by involution or in the deleted product.
This actually lives in the it is also, you can take it as a chain also up there, but we can, for now, because this theory works for the usual homology, it's a cycle in the quotient. Okay, what I meant was that because this is a cycle, so wherever you find this cycle in any quotient, then your complex will be non-embeddable. Okay, now there are multiple. Okay, so now this approach helps us to actually prove that.
Well, sorry, you probably mean that by this last sentence which you said, you probably mean that if you find the double cover of Z in the deleted product of some other complex, and it is embedded there equivariantly, then that other complex also doesn't embed in R2N, right?
Yes. So if the other space is a quotient of the deleted product.
If you just find Z in the quotient by the deleted product, maybe it's not enough. It's not clear.
So let's see. But there is some chain up there, right, that maps here to this chain that we have found. And I think, yeah, okay, so yeah, I don't have proof right now, but I think it's enough to find it in the. So if there is a chain in the quotient, then there will be a chain which is which corresponds to this in the up there, and.
But okay, but then you need an extra condition about the fundamental group, I think. So you need to fix a homomorphism from the fundamental group of Z of this cycle into that modular 2, and this homomorphism should commute with the embedding. I mean, you can also speak about maps from this cycle into RT infinity And this map should commute with the embedding of Z in the motion by evolution of another deleted product.
Okay. Yeah. Okay. So let's move on. I'm not sure, but yes, it needs to be more conditions on the. Yeah, but I don't know right now what are those conditions. But I explain what I meant right now. So let's okay, to be correct, let's take this Z to be in. So if we take this Z to be in the original space, not in the quotient, and this is some subcomplex. So if this Z prime turns out to be let's say some subcomplex of okay, so let's say L. And it is equivariant, as you say. So this embed is mean it. So it will be equivariant, right? And so if we look now that on the intersections between on the intersection homomorphism on the cells of this cycle, this still has to be an odd number of intersections. Because the fact that the intersections are odd depends only on the subcomplex. It does not depend where it lies.
You mean that the value of this one complex co-cycle on this cycle is not zero? Is this what you mean by the number of intersections?
Yes. But that is also the number of intersections between. So you count the. So this Z prime is product of cells like this, which are disjoint, and this value of phi on this is the parity of the sum of the intersections. And this is odd, and it has to be odd, I mean, regardless of. Do
you mean that you take a general position map into R2N and look at intersections there?
Yes, for instance.
Intersections of top-dimensional simplexes and n-dimensional simplexes, right? Or d-dimensional.
Yes, top dimensions.
Well,
yeah, here I'm using the definition of the abstraction, also using the intersections, the intersection homomorphism.
Yeah, so you can this abstraction, this one complex abstraction can be defined by just counting the modulo 2 one complex abstraction. Yes, can be defined by counting the intersections of this d-dimensional simplexes disjoint pairs of disjoint d-dimensional simplexes in R2D.
Mm-hmm. Yes, actually here I didn't want to go into these things, but I just wanted to say that we can look at this somehow to the dual class. Whenever we have Z2, there is duality, and then we can look always at the dual class of the Van Kampen abstraction, and it gives you some kind of a chain or some kind of a homology abstraction. So, but I don't want to, I will not use this. Okay, so this is, so I won't discuss these things anymore. What I want to discuss.
Sorry, is that the idea from between a Kleiner Topology or is no?
Yes, yes. So yes, so that was what I wanted to say, that if we use Z2, then now if we want to apply this idea to the join, to the embedding of the join, we have this. So remember these spheres where the join gives you also spheres. And it's also true that whenever you have these kind of abstractions, which are complexes, their join gives you also abstractions. And so you can, using these subcomplexes, as Sergey said, so Besvina-Kopowich Kleiner, so they say that, so they show that if these, so let me write here. If the mod 2 abstractions are non-zero, then the mod 2 abstraction of the join is also non-zero. They almost show it, but it's not exactly like this in their paper. But this in this case is simpler. So okay, now what I want to prove is the general situation where we have the integer abstraction instead of mod 2. And now if we can find something that works like these subcomplexes, which are abstractions. Actually, I thought before knowing this paper of Besvina-Kopowich Kleiner about this approach. And so what we need is something like the following lemma. So if you take any chain complex of free abelian groups and you take any torsion cohomology class, and these abstractions are, Van Kampen abstraction is torsion cohomology class, then your class is not zero if and only if there is an integer n and there is some chain C such that the boundary of your chain is zero. So you have some class H, which is the class of some cocycle phi, and this is torsion. And you want to show that you have to come up with some chain which certifies to you that this class is non-zero. And there is such a thing. And if you have some C, there's always some C and some N where boundary of C is zero modulo this N, and phi of C is not zero modulo this N. And this condition tells you that phi is not a coboundary modulo n, and therefore is not a coboundary in integers. Right? So another way of looking at this lemma is try to compute homology with let's say P. So this lemma is true for modulo P, right? Modulo a prime number. And now for other cycles, for other cohomology classes, also you can keep computing the cohomology with power with P, and then with coefficients, with modulo P2 and modulo P3, and like this. And you eventually your cohomology class will be non-zero for some.
Sorry, but I don't understand why it is true for if H is two torsion. How do you prove this lemma when H is two torsion, like the one Compton abstraction?
Yeah, so I give an example instead of proving, which is perhaps, I think it's more useful. So consider the RP2 . So we can form RP2 by one, so let's say 1 0 cell and one cell and another 2 cell. So we attach these 2 cells by a map of which maps this boundary by degree 2 map. So this is E2. Now the cohomology of RP2 we know is this is Z in dimension 0 is 0 here. There is a Z2 in dimension 2 and also a Z. No, actually there is only a Z2, right? Okay, there's only a Z2. And this Z2 here is generated by contains the cycle, the co-cycle which assigns 1 to this E2. So let's say E2 hat, for instance. Now if you compute modulo 2, the boundary of this E2 is 2 times E1 is 0 mod 2. And the co-cycle which assigns 1 to this cell assigns a non-zero number to E1, which is a mod 2 cycle. And therefore, so this shows that, so this is not 0 to modulo 2. And in general, also a similar situation happens. So the torsion cohomologies of dimension n they come from torsion homologies of dimension n minus 1. And so okay, so let me, okay, another way of trying to see this, why this is true, is by computing the cohomology starting with modulo sum prime p and seeing if this H is not 0. Okay, so let me give you this proof. Oops, sorry. So let's compute the reduction mod P of our H. So let's say R sub P is reduction mod P. Okay, if this is not 0, then you can, so because P is prime, so again duality exists and these certificates exist. And if this is 0, but H is not 0, then H is P times some H1, right? And this is true. And you can do the same thing to H1. And now either H1 is 0 modulo P, or H1 will be P times some H2. And if you continue like this, so you can write H as P to the K times HK. Now this has to stop at some point, and it will stop when this HK becomes actually non-trivial modulo P.
Why does it have to stop at some point?
So yeah, so the reason is that so H is non-trivial, right? And so if you look at the boundary matrix, so you want to co-boundary matrix. This solution does not have a solution. Sorry, what was your question?
I guess, so if it doesn't stop, then it means that H is infinitely divisible.
Yes, yes.
And if you're, which could happen, but if your complex is compact.
Finite, yes.
So
yeah, so let me.
It still could happen. For example, torsion modulo 3 is infinitely divisible by 2, yes?
Yes, but for 3, no. So it's for every class, there's a different P that works for it. And so another way of saying it is that, so let me raise this so this will not, it's easier what you said. So the maximum number that can appear here is if we write D in the Smith normal form, the diagonal form, the max that can appear here is the product of these guys, product of the diagonals. because because you are saying that, so because remember, these are torsion classes. Okay, so I remember now. Okay, so these are torsion classes, and for H, and all of the torsion classes, if you look at the let's say, this D, this co-boundary goes from some ZK into ZL. So then this space, the torsion elements that appear here, they have some maximum. I mean, they are finite. So this is a finite. So the totality of torsion elements, they form a finite group. So they cannot go to infinity. Essentially because you don't have infinitely many torsion homological classes. But the proof works by, so I won't go into details, but you just write, similar to this, you write the co-boundary matrix, and then essentially you separate so you pair the cochains to co-boundaries, and so you can, it's not difficult. And it's similar to, I haven't seen this lemma anywhere, but it's similar to the lemma that says, if it is in Hatcher, I think, that if you compute homology, if homology is 0 with every p, when you compute it with any prime, it's 0, then it's 0 with integer coefficients. It's similar to that.
Yeah, I guess one can say that in a finitely generated abelian group, you cannot have an element of order 2 infinitely divisible by 2. That should stay.
Exactly. So because if that is true, then there would be infinitely many torsion elements, because each of those divisors are also torsion elements.
Yes.
Okay, so now you consider these are chains. So these chains, we can take H to be the Van Kampen abstraction, so the integer Van Kampen abstraction, and these chains, then they certify that the Van Kampen abstraction is non-trivial. And no, previously we had complexes, but these are just like complexes, but with an integer attached to each cell or oriented cell. Okay, so now using this approach, we have a way of certifying or displaying some chain that in our complex in the deleted product shows that our complex is not embeddable. But actually, we want such a thing not in the deleted product, but in the deleted join, right? Because we want to use this something similar to the Grunbaum theorem. So we want that the join, because of the join of the deleted joins formula. So if you have objects in here, if you have abstractions in here and abstractions in here, then we can hope that the join of these objects, this will give us an abstraction into the deleted join of the join. But right now we have in the deleted product. So the first thing we do is to actually use deleted join, means cohomological abstraction in deleted join instead of deleted product. And for that, we use a okay, so we want to assign some class, which I denoted with A of the deleted join. Such that K embeds into R to the 2D if and only if this A is 0. And we want this to be true, for instance, for the greater than or equal to 3 at least. And then imagine we have such a thing, then we can use these chains as abstractions and then try to find up somehow an operation that joins these abstractions into an abstraction for the join. For this purpose, we also need to have this property that A actually is such that this abstraction is such that we can write A of the join oops, no, 2 I should put there, delta I should put here. In terms of okay. But the definition of the Van Kampen abstraction that I gave, it actually is not very suitable for this.
Well, you can take the same approach just with twisted coefficients, and it will give you the abstraction and the weighted join.
Yes, exactly. Yes. Yeah, and we will do that. But I will use instead the Smith class of dimension 2D plus 1, which is similar, but it has an additional benefit, which allows us to compute the class of the join in terms of the factors easier. I mean, than the Van Kampen abstraction, because if you recall, the Van Kampen abstraction depends on this f, either depends on a function f into R to the 2D or into S infinity, so or an equivalent map into S infinity. But people have actually made the definition of these embedding classes independent of these maps. And the result of making these definitions independent of these maps is actually the Smith class. And so these Smith classes give us a way of, independently of any function, define these abstractions to embeddability in both joins, deleted join and deleted product. And that's why I use the Smith classes, because they have a definition that is independent of any function or any other external thing. And it also then, because of this property, it's then straightforward to compute the the classes of the join in terms of the classes of the factors. Okay, now the properties that we need from this Smith class, and I define this A, which is the abstraction, is the Smith class of dimension 2D plus 1, which, as Sergey said, it is some kind of an analog of Van Kampen abstraction for the joint. But I want to have two properties, which helps me a lot. So, but now I work with general complexes. Let's say M be a Z2 complex. So by M, I denote a Z2 complex. And then we have one Smith class per dimension. So we have AI of M. Okay. So these live in different cohomology classes, so cohomology groups that I explain later. But for now, the properties that we want is for them to be stable under suspension. By this, I mean that I of M to be not zero if and only if so S of M is suspension of M, and I want that I can move one higher dimension by, I want to use suspension for going into even dimensions, essentially. And the second property that I want is that if I have something of dimension 2m and this class of dimension 2m, I want to be the complete abstraction for existence of an equivariant map to -1. And this is true for the equivalent of Van Kampen abstraction in the joint also. And so this is already verified, for instance, by a theorem in Sergey's paper on Van Kampen abstraction. This is also is the first thing that so the reason this is good, because in even dimensions, so these things are all equal. So this will be equal to the usual cohomology abstractions for the embeddings. And this will also I prove in my paper, and I use it. It's very helpful, for considering odd and even dimensions somehow uniformly. Okay, so now consider assume we have these two properties, and then how to actually make sure that this is a abstraction to embedding. Does this Smith class of the dilated join work as an abstraction? So we can show that by a sequence of arguments. So I don't know, maybe Sergey has a better argument here, but I would show it like this. So if we take the 2D plus 1 dimensional Smith class of the dilated join, this will be zero if and only if. So I go one dimension higher, by suspension. If this is 0, and then because that's even dimensional, there will be some function from the suspension sorry. So there will be some Z2 function into Z2 map S to the plus 1, and this is again if and only if there is a map. I think here we need some k greater than or equal to 1. So sorry, D. And now we remove the suspension by the equivalent suspension theorem. So whenever the dimensions is good, so you can actually go to one level down. And I think here we need D greater than or equal to 2. And then this is if and only if there exists another function from the deleted product into S to the minus 1. So this part has been something which was showed by Skopenkov, Arkady Skopenkov, and it's a, I mean, here to here, I mean, this one. And you can find it in this paper. So which is an archive. And this step itself has 3 steps. And I think here we needed also D greater than 2.
Which paper?
So this is a paper, an archive is a short paper we have written. I have written.
What year? So it's recent paper.
It's 2020.
Well, this was known long ago. Like in my paper 10 years ago, this is proved.
This exact thing?
Yes.
Okay,
last, yeah, the last equivalence.
Okay, so this is also core, but also there is something, I think in the Skopenkov there's also a proof, almost proof in this paper of, which is, which contains this cone lemma. I don't know which year it is, but it's very old.
Yeah, it could be that he also proved it 20 years ago, yes.
Yes. Yeah. The main part is actually in here.
But what are these Smith classes? In which cohomology do they live? Integer cohomology?
I will talk about that later, but I just want to show that, I mean, by this sequence of things, we can use this object as abstraction to embeddability into double dimension, right? Okay, now I go to defining these A's. Okay, so this, okay, now what are these Smith classes? So let's have, as before, M to be a Z2 complex. And then I show the action of this by T. And then we have also T sharp, which goes from the chain complex to the chain complex. And T sharp, again, which goes from the cochain complex to the cochain complex. And I also show these guys with T later. So we can now define 2 spatial homomorphisms. which is D to be 1 minus T, and S, which is 1 plus T. And then we say that some chain, so C okay, I work from now on with cochains only. So these things you should think of in cochains. So if they are essentially this, so these are also some dimension here, but I won't write these dimensions and these signs for simplicity. And now let's have some phi in some cochain. Now if D of phi is 0, then phi is T phi. So what does this mean? This means that for any chain, phi of C is equals to phi of T of C. So essentially phi then is equivariant. So it gives the same value to chains in the orbit of T, orbit of Z. So so therefore the kernel of this D we show it by C sub D of M, and it's called the D cochain. And because these they are equivalent, so the value of phi depends on this orbit, then this is actually isomorphic with the chain complex, cochain complex of the quotient. So if this quotient is, let's say, is a complex. Okay, so we have therefore these D cochains.
Well, I think it depends on the parity of the dimension. If the dimension is even, then it is isomorphic, and if the dimension is odd, then it is isomorphic to the for chains with twisted coefficients.
But I think these are isomorphic in any dimension. But
well, okay, as groups they are isomorphic. But when you take cohomology,
yeah, I'm not talking about cohomology right now, so I will talk about it later.
or the boundary homomorphism is not exactly the same.
Okay, so if you take these D cochains, so you can take boundaries in also. So you restrict your original boundary into these D cochains, or let's say co-boundaries, sorry. And then you have a chain complex of D cochains. And if you compute the cohomology of these, then I denote that cohomology with HD of M. And this is called the special D cohomology. Okay, so we have special decohomologies for every dimension. Now we can do this also for S chains. So for a chain, for a cochain phi, so if S of phi is 0, so then phi of is minus, sorry, is minus T phi. It means that phi assigns opposite values to a chain and its image under T. So totally similar to before, we write kernel of this S to be as our S chains, and then we restrict the boundary, and then we have again, or rather co-boundary. Over these S chains. And the homology that we obtain here is we call it spatial S cohomology. Okay. Now the properties of S and D, which are very important, also I write it here. So the combination of these homomorphisms is always 0. And if you take SS twice, you get 2 times S. And D is also is 2 times D. So these are some properties of these. And now there is a very important relation, and that is that if you look at the kernel of let's say di, your I-dimensional D cochains. So this is actually equal to the image of S dimension I. So in other words, if phi is a D cochain, you can write it as S of some psi. Essentially, you take some chain and you apply it to images. You take one. You assign a value. You choose a value for one cell in an orbit, and to the others you give the same value. So this is this S operation. So it just copies the value of psi to everywhere. And similarly, kernel of psi is the image of di, which means that I write it here. If phi is the S cochain, you can write it as D of something. Okay, now having this, we go to define these Smith classes. And for that, we start with the cochain, which is 1 in the zero-dimensional cochain group of M. So this 1 is the cochain that assigns 1 to every vertex. And we can see that this is a d times 1 is actually 0 cochain, because every edge, has 2 vertices with opposite signs, and so, and this object is a D cycle, D chain. Actually, is a. Oh, actually, what I said was the coboundary. Sorry, it's the coboundary of 1 is 0, and also D. Also 1, we can write it as S of some chain, because when 1 assigns 1 to every vertex, so you choose a fundamental domain of your vertices, and then phi is a cochain that assigns 1 to a fundamental domain and 0 everywhere else, and then S phi will be 1, because S phi is phi plus T phi. And because, okay, so I denote this phi with phi naught. And let's define A naught, so the zero-dimensional class, the Smith class of M, to be the decohomology class of this chain, which is S phi naught, which is the same as 1, right? So now let's look at the coboundary of phi naught. So if now we compute S of coboundary of phi naught, this will be coboundary of S of phi naught. And because S of phi naught was 1, is a cocycle, this is 0. And therefore, coboundary of phi naught is a S cochain. And we can write it as D times some phi 1. And we define A1 of M to be the S cohomology class of this D phi 1. And we can continue like this, and we obtain a sequence of these cohomology classes, co-chains, with the following property that I will write here. In an even dimension, coboundary of phi 2i will be D times phi of 2i plus 1, and coboundary of phi 2i plus 1 is S times phi 2i plus 2. And this sequence is called a resolution of 1. And we define a, okay, so I write it here. So the Smith class of an even dimension, therefore, will be the dechromology class of this object of the even dimensional chain, cochain in this resolution times S. I mean, S applied to it, and then you take the dechromology of this, and the odd dimensional would be take the odd dimensional chain in the resolution, we apply D to it, and they take the S cohomology class. And therefore these, yes.
Well, I think I can define these classes in a more, so to say, invariant, so to speak, way. So if you don't mind, I can try to give a different definition. I mean, it's equivalent, just the same as what you said in a different language, if you want.
Okay.
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 One moment. So maybe I will need to.
I stop my sharing.
Well. Thank you. Okay, so we have some complex. How did you call it?
M. SZ2
M, yes.
Yes.
And so there is a double cover. So there is M and M modulo the involution, right? Was this your notation?
Yes.
Okay. So then we have we take some triangulation of this quotient, and then there is triangulation of this M, which such that the double cover is simplicial.
Yes.
So then we have chains of this quotient and chains of the double cover. Now, on these chains, we have the action of T. And then there is the subgroup which is invariant under this action. Well, how did you call it? D subgroup, yes?
Yes.
Maybe I write equivariant because I'm more used to it, but this is same as D. And then the quotient, yes, and also there is another subgroup which is so to say skew equivariant, which was the other S. But let me write as skew equivariant. So when you take the action of T, it changes the sign. Yes, there are such chains, and then the quotient by one of them is isomorphic to the other one. The C equivariant is isomorphic to C Q equivalent.
Yes, that's true.
And
or in another, that's true.
The other way around.
That's true.
If you take quotient by this Q chains, you get the.
It's true. Okay.
So there are short exact sequences of chain complexes. These equivariant chains go into the usual chains. So this is all for this double cover, and then go into skew equivariant chains, and then zero. And another one, skew chains go into all chains and go. Okay, sorry, this was yes skew, and this is equivariant. Okay, and the same for cohomology, but maybe we don't need for cohomology this short exact sequences of chain complexes if long exact sequences in homology and in cohomology.
Yes, that's true.
So in cohomology, we are interested in cohomology. So let's write in cohomology H equivalent of M goes to usual cohomology. In cohomology, I should write it like this. All cohomology of M, and then Q equivalent cohomology. And well, yeah. Okay, so then there is equivalent of the next dimension. And this is a connecting homomorphism, which I think is the same as what you had.
That's true, yes.
So now we can just take indeed. So this cohomology group is just the cohomology group of this chain contour, or the dual chain. So we take one in H0 equivalent, I think. Yes, equivalent. And then apply this delta as many times as we want. So this delta goes from skew to equivalent, and also in another such sequence, well, another sequence looks just like this, but opposite. So skew go into O, and then go into equivalent, and then go into skew. So the next dimension. Okay, so this is another connecting homomorphism, and you apply it. You apply them first one, then another, then again that, and so on. And you move between these two groups. But now there are some remarks. So this group equivalent is isomorphic to the usual cohomology of M modulo the involution.
That's right.
And this one is isomorphic to the usual cohomology of M modulo involution with the twisted coefficient.
What is this ZT?
ZT is the twisted coefficient, so it's like a locally constant
Okay.
quotient, so that when you go around the loop, which doesn't lead to M, then the sign changes in this talk.
I say you mean what they call the twisted integers, I think, right?
Twisted integers, yes.
Yeah.
Twisted by this involution. It's a local coefficient system. And
exactly.
You can write this for RP infinity. So M as M, we can take the sphere, infinite dimensional sphere, and then this is RP infinity. Yes, so we have this all the sequences for RP infinity, and one can compute that cohomology of RP infinity with the twisted coefficient is always Z2. Or in other words, you can say that this Q cohomology of S infinity.
Sorry, we can see your paper.
Thank you. So the Q cohomology of S infinity is also Z2 in all dimensions.
Yes.
And so we can just take the pullback. Oh no. No, sorry. It is not. If n is odd, if n is odd, and if n is even, it is 0. And for the other group, so this is this Q or twisted, and for the usual cohomology, it's opposite. Yes, so the usual cohomology of RP infinity
Yes.
is 0 when n is odd, and z modulo 2 when n is even. So in even dimensions, we can look at the cohomology of this quotient with usual integer coefficients, and yes, we have the arrow goes in this direction. And we pull back this generator in even dimensions. And in odd dimensions, we do the same, but with this twisted group, and we pull this generator back here. So it's really the same as
Yes.
what you said.
Yeah, I agree. And actually, the way you explain it is I think is the also in terms of the general situation is how it is explained in Wu. So so you define these corresponding to this delta that you have. There is, I mean, this co-boundary homomorphism that you have. There is also what is called the Smith homeomorphisms, which goes from decohomology into S-cohomologies and S-cohomologies into decohomologies. And you can also define the general situation exactly like this. I mean,
Yeah,
you did it for Z2, but actually for the general situation also there is a similar definition. And this is actually in Wu's book. I mean, the first part of your, what you, is the classical way. And I try to give a definition which I think is simpler and is also more helpful for later, for some calculations later.
and one more remark. So this Smith classes. So as you say, the A to N lives. No, A to N lives in this group. Odd lives here, and even live here, and odd live here. Yes.
Exactly, yes.
They are this pullbacks of these generators, or alternatively, they can define just by iterating this coboundary on one. So there is a third definition of them, which is that so we have this double cover, and we can take the line bundle from some x associated to this double cover, and then this double cover, this line bundle has an Euler class, which lives in one-dimensional cohomology, this with twisted coefficients. Then you can take a direct sum of C, so C to the n, which is C plus so on plus C, an n-dimensional vector bundle. And then the Euler class of this C lives in the n-dimensional cohomology with coefficients which are twisted depending on the parity of n. So you can say that it is the nth tensor power of this shift. So when n is odd, this is an orientable bundle. When n is even, this is an orientable bundle. And then this is the usual class, the usual Euler class, which lives in integer in cohomology with integer coefficients. And when n is odd, this is a non-orientable bundle. It can be non-orientable, at least. And so this is the twisted Euler class for non-orientable bundles, which lives in cohomology with twisted coefficients. So this is an internal definition, which doesn't require any maps into infinity.
Mm-hmm. Thank you.
Thank you. Now I hope if there are no questions.
So how much time do we have? So I think we are finished.
I think maybe it's time to make a break. What do you think? Or maybe you can say.
I need some maybe 20 minutes more, and that's it. I'm okay for we can do a break, or I can explain. I try to explain what is left maybe in 15 minutes. Actually, I can do it maybe in 15 minutes.
But maybe we don't rush, so we make a little break, like 15 minutes, and then we continue like half an hour, as much as we need.
All right, then okay. So let's have a break for 15 minutes. All right.
Okay, so we continue then at 7:20.
Yes.
Hi, Salman.
Yes.
One thing which I forgot to say is that these Smith classes, one advantage of considering them downstairs at the quotient by involution is that they become just all powers of A1. So A2 is A1 squared, A3 is A1 cubed, and so
Yeah,
on.
but that is true in Z2. I mean, I think that's true in for actions of Z2, and also I think for Z2 coefficients.
For integer coefficients. I mean, you have to do it with twisted integer coefficients. So
Yes.
when you take uh, uh, even powers of a class with twisted coefficients, and you go into non-twisted coefficients, and when you take an odd power, you go into twisted coefficients again.
Yes. Yes. That is in. So there is this cup product. So it's a kind of a different cup product, which I think Shapiro already has it in his paper. He explains this. Yes, that exists. Yes. So, and are you going to give some argument based on that actually here? But I say these definitions because I think this definition is what is most useful for me. And so the other ones are perhaps, I mean, as you said, they are more, I mean, they are more useful in other applications. But because here I want to actually compute the classes for the join, I mean, the best approach for me was to actually start with these guys. Because when we start with one, then if you have the class for one, then you already have the rest. So this is actually, it was easier for me to define it using a resolution.
So I also had a question about the lemma, which you discussed some time ago. So in that lemma, so you had, for example, let's consider the case where we have a generator of Z modulo 4. Okay, so it could happen for the one company abstraction, right? So the one company abstraction could be it could be no, not the generator.
Yeah, so let me say it like this. So the one company abstraction will be the top of these powers of 2, right? So there will be 2 to the sum k, which is the one company abstraction, and twice that will be 0.
Yes,
And, and there will be some chain where this one company abstraction gives something which is not 0 mod 2 to the k actually. I think it gives the value which is to the k, I think.
okay, so if you divide the one company abstraction by 2 in this case, then it will be an so then it can be reduced modulo 2 and it will remain non-zero. Okay, then you have this
Yes.
modulo 2 chain on which this class doesn't vanish, but this this is a cycle modulo 2. So if you do this cycle with integer coefficients, then maybe it's not a cycle. Yes, and
No, it's never a cycle. It's a cycle modulo 2. It's not a
yes,
cycle.
it's a cycle
Because
modulo 2. And then you evaluate not the one company abstraction on it, but the one company abstraction divided by 2. So what and in your lemma you were going to evaluate the one company abstraction itself on some side. So this
yes,
is something I don't understand.
yes. So I think the situation is that if you look at these uh, so there is a primitive element, right? As you said. and then there is powers of 2. So for instance, there is some eta, and there is 2 times eta, 2 times 4 times eta, etc. And the topmost, the non-zero class is actually the Van Kampen abstraction. And now I think, if I remember correctly, the certificate for all of these is the same class, but they assign only different values to it, which is non-zero mod actually 2 to the k plus 1.
Yeah, this is something I don't understand. So I understand that the generator evaluates to non-zero on this chain.
Okay, let me give you a geometric example. So in the complexes, I think you will stop. So do you hear me? Oh, okay.
Yes.
Yeah. So in the complexes in your paper that you constructed, when the abstraction is 0 modulo 2, right? Then there is always chains which are actually, they have the abstraction is the number of self-intersections is 2 times something. So it's an even number. Those are the chains. I mean, exactly your construction, I mean, your complex gives us that chain complex on which the Van Kampen abstraction, which is 4 torsion, actually gives an even number to, but that even number is 2. And because it's not 4 and it's 2, it actually certifies that that class is not trivial.
Okay, I now see. So you have this modulo 2 cycle, but you consider it as an integer chain, and you evaluate this Van Kampen abstraction on this integer chain, and it should be non-zero because it is an integer. When you evaluate, you go into integers. So the generator eta evaluated to 1, say, but then the Van Kampen abstraction on the same chain will evaluate to 2. Yes?
Exactly. Yes.
Okay, I see.
But this chain is actually a co-boundary with a boundary with the top coefficient. It's a boundary modulo the top coefficient. So let me draw this. So you imagine instead of in RP2, instead of a map of degree 2, having a map of degree 2 to the k, for instance, when you attach this cell, then exact same cohomology class will assign 1 to this 2 cell. There is only a single 2 cell, and so the generator eta will assign 1 to that, and then 2 eta will assign 2 to that, and the 3 eta will assign 3 to, and you have all the way to the. But the certificate itself is a co-cycle modulo the top coefficient. I mean 2 to the k plus 1 actually. Modulo 2 to the k, sorry. So the same cycle, which is a certificate for the top class, for the Van Kampen abstraction, is also certificate for the below classes.
But are you saying this is a cycle, not just modulo 2?
Yes, but modulo the top element that you have, which is non-zero. Modulo the coefficient in which the Van Kampen abstraction is not 0.
This is not so obvious.
So let me go to my
Yes.
notebook. I can draw an example here. So you see, let's say again have this edge here. So now we have this chain, and if now we attach it with a map of degree 2 to the k, right? And now we look again at this. So now the cohomology here will have elements of order, let's say, up to 2 to the k, right? So there will be eta, and there will be 2 times eta, and all the way to, I think 2 to the k minus 1.
Well, I see that in this case you have a cycle modulo 2 to the k. But
this is always the case. I think this is. Yeah.
Okay.
And I think if this was not because of this, it would be a different situation. And this is actually
So
something which has consequences.
are you going to use it that it is a cycle modulo 2 to the k?
Yes. Well, maybe. I'm not sure yet, but maybe. I'm not sure. But let's go through the argument, because I look at it in a different way. And for the fact that the abstraction will be 0 for the join, we don't need this. But the value, okay, I remember now. So the value is always, there is some chain where the abstraction gives the value 2 to the k minus 1 to that chain. And exactly because of this, because this is, and let's say V is the abstraction, is also 2 to the k minus times eta. So eta has to give the actual, the value 1. So
Okay.
but maybe there are other cycles on which eta gives, which are only mod 2 cycles, and eta is 1 on that. That is true. But there is this bigger cycle also works as a certificate for eta. I mean, the cycle which is certificate for V.
Okay, maybe we continue.
Yes. Okay. So we were. Okay. So Sergey mentioned 2 other definitions of Smith classes, but I use this definition because it already gives you a very simple way of computing it. So you simply start with this one, and you have these choices. So see that every time that you want to write, for instance, 1 as a S times some other chain, you have a choice here, right? So if you are interested in, I mean, in the intuition, so these choices actually correspond to the different fundamental domains that you can choose for your cells of every dimension. But it's not still uniquely defined. You have these choices still in when you want to write something as an S times some other chain or D times some other chain. You have a choice here, and these choices gives you different resolutions. But those different resolutions always give you the same classes. And this is also a nice property that allows us to play with these resolutions and get some nice results. And the Smith index is you look at these Smith classes, and they are non-zero up to some dimension. And then, for instance, let's say this is the last one, is some j, and the j plus 1 then is the Smith index of k. So it's the first integer where the Smith class of that dimension is 0. Now, we want to compute the Smith index inside actually a join complex. And for that, we want to, first we need to write the chain complex of the join in terms of the chains in the of factors. And this is actually possible if we if you take from now on, imagine actually that K and L are Z2 complexes. So I don't talk. So let's take K and L to be Z2 complexes. Then we have the chain complex for K and chain complex for L. And now we can actually write a formula for the chain complexes of the join. So if we take these to be augmented, So we need this augmentation. And then there is actually a formula for the chain complexes of the join as a transfer product of these factors, chain complexes of these factors.
Augmented, you mean you add something in dimension -1?
Yes, and you also I denote that by empty cell, and we also define this. And this is the only choice that actually works. And now the difference with the usual, so people do it usually for the product. Now the difference here is that you go one dimension lower, such that so this dn is the n is the chain complex of dimension n, and you sum over the tensor products of chain complexes where the summation is actually n-1. So usually you do n when you have product, but because it's joined, you take n-1. And empty is counted of dimension -1. And the boundary on this, so if you have a boundary, if you have some sigma is like the boundary formula on the product, but it's here you write the dimension of sigma +1 actually. And simply you should think of this as the join actually of sigma and tau, and you write the standard formula for the boundary of the join. It gives you this. But for the empty boundary is 0, of course. And for each vertex, the boundary is this empty set. And anyway, so people use this also before in different places. So there is a way of essentially the chain complex of the join is a transfer product of the chain complexes of the factors, but with some dimension deficiency, which is here. Okay, now this also similar is true for cochain complexes. So there's an isomorphism between the home of this cochain complex and the cochain complex of this chain complex and the product of a tensor product of the cochain groups of these individual chain groups. So,
I suppose this should be in the formula second from the bottom. It should be DC at the end of the line, yes? At the end of the lower.
This one?
Not between them. Yeah, at the end it should be DC, yes?
Ah, thank you, yes.
D tau maybe.
It's actually
D tau, yeah. Yeah, I mean D, yeah.
And so the cochain, we can also write this. So it means that if you want the cochains for the join complex are essentially you take the cochains of the factors and you make the tensor products of them. And when you want to compute this on some sigma tensor tau, it simply is the value of the first one you compute on the first, and the second one you compute on the second, and then you make product. And so now we have this relation between the chain complexes and cochain complexes, and we also have one. So what is one? So the one of K join L sorry, we are not in there anymore. So each of these K and L are now actually themselves Z2 complexes. Is you take the empty set, make the product of it with sign up, plus you take the fine up and make a product of it with the empty set, where one of K is S of finite and one of L is S times sign. So remember, these finite and signate, they give one to vertices in a fundamental domain, right? And this empty set joined with a vertex is just a vertex. So this object, so this chain gives one to vertices in a fundamental domain of one factor of L actually, and this one gives one to a fundamental domain of K, and together a summation of them is a chain which gives one to vertices in a fundamental domain of the K join L. And it's true then that now if this S is now the is S of the join complex. If we apply it now on this guy, this is one of the join complex. Sorry, this is S of this. So I wrote it again here. So in other words, we have our first term of the resolution. So if I will show you this capital phi, the terms of the resolution inside the cochain complex of the join. And so we have the first term of a resolution, and from here it's now we need only the S and D of the join complex to compute the rest of the terms in the resolution. And we can do that, and if we do that, we get the following formula. So it's a tedious computation, but the resolution term of dimension J is a summation of other terms, essentially J plus 1 other terms, J plus 2, where depending on if this J is even or odd, it has two forms, so which we see here. Now, this is for the general case where we have the action of ZP. When we have an action of Z2, this formula just says that you make the product of the terms of both resolutions, that the summation of the dimension makes sense. You want to have J-dimensional term in your resolution, you need to make a product of the terms in the factors, resolutions in the factors, whose summation of the dimension is actually J minus 1. And now with sometimes a T applied to one of them. So sometimes you need to do some twists. But in general, the form of the formula is like this. So now based on this formula and we have already for the resolution for the join, and we have certificates for each factors, and then we can hope for that the join of these certificates, which is actually something like so if you have some C1, which is a certificate of, okay, for the Smith class in one factor, and then we can make a tensor product of it with the certificate of the Smith class in other tensor, and we can hope that this is actually a certificate for the join. And it turns out to be actually true almost. And first of all, what also we need is to have some kind of a analog of that lemma that we discussed about the certificate of the homologies for homologies of the dehomologies, decohomologies, and S-cohomologies in terms of the chains in the double cover, essentially in the join itself, not in the quotient. And it is possible. So there are conditions on chains that you can have that they can serve as a certificate for these D and S cohomologies, and they actually live upstairs, and so it's easier to work with them. And for instance, for decohomologies, it's easier. If you just look at the chain, which is the certificate for, I mean, in even dimensions, when it's a certificate, for instance, for the Van Kampen abstraction downstairs for the Smith class in the quotient, you can just take the image of this upstairs by this, I think it's called a transfer map, which if you take a sigma, so let's say a cell of so the class of sigma is a cell in K divided by T. Then there's this operation that sends class of sigma to sigma plus T sigma. So this is the chain isomorphism of the quotient and the D chains in the double cover or in the actual Z2 space. And so these things, they can work as also as certificates for to show that these D cohomologies and S cohomologies are non-zero. So anyway, in brief, so there are these chains, and this is actually true that if they are, if the Smith classes are non-trivial mod P, then this approach actually works. I don't go into computations, but they are straightforward. But the approach is that you just take the cochain, the chains that shows your factors are non-trivial as a P cohomology class, and somehow make a combination of them. Then it put this in these formulas, and it is true that you can show that these the class of these terms in the correct term, the resolution has to be non-zero. And also note that this formulation is independent of the dimension of the complex. But now I want to say something about the case where they actually, when both of these factors have zero classes mod 2. So let's say we have okay, we have K and L now, so we have some I, K, or some Smith class of this is 0 mod 2. But this is not 0. And we have also some other A. And when this is true, we can write this. I show this with A. So we can write A as 2 times some other class B, where B is non-trivial. And imagine I is even. And then we can write B, because this relation is actually true in Chromology. Then B is the class of some S eta, some D cocycle, where we compute the Chromology. And now let's also phi be, as usual, the resolution for K.
But maybe you can say which complexes are we looking at? What are K and L?
So K and L are Z2 complexes. And AIK is the I-dimensional Smith class, and AIL is the L-dimensional Smith class. So
are you saying that in any such situation, when the both one company abstractions are 0 modulo 2, but non-zero as in general?
integers. Yes. I'm considering this case now.
Then in any such situation, for the join, the one company abstraction will be 0. You don't need any additional assumptions.
I'm trying to show that yes, essentially. So yeah, I'm going to show that.
Okay.
And the way I do it, so maybe there's other ways to do it, is to so I've done it for the general P, and so this approach that I write it works for general action of CP. And so because A is 0 mod 2 and it's non-zero, we can write it as 2 times some B, where B is non-zero, and B is also a Chromology class and is therefore a class of some S eta. Now we can change this resolution into another resolution actually with up to, so we get the same objects up to dimension phi I minus 2. Then I will choose some different phi I minus 1. And so and this is therefore A gives us, A is 2 times the class of 2 times S eta, and also is the class of S of phi I, and this gives us there is some cochain like B where the difference between these two is S times is coboundary of SB. Now I say phi tilde I minus 1 to be phi I minus 1 minus SB. Now if I compute the coboundary of phi I minus 2, you will see that it will be this up to here is correct, will be a correct resolution. And after this, you will have coboundary of phi tilde I minus 1 will be coboundary of phi I minus 1 minus coboundary of SB. This gives us S phi I minus coboundary of SB, which will be 2 times S eta. This is equals S times S eta. So therefore, we can choose for the next term in our resolution this S eta. And now observe that this is a cocycle. And because it's a cocycle, the things which are higher than this will be 0, the other terms of the resolution. And now with this, we can do it similar to this for L. And now we have two terms of the resolution. If you go to this formula, okay, I actually have this computation. Right, so if we actually look at the relevant term of there is only one term which can be non-zero in this situation. Okay, let me say this also, that if in the situation of this here, this AI has to be the top dimensional class where is the highest dimension where the Smith class is non-zero. In other terms, if we have this situation, we have the Smith index of K has to be I plus 1. So in other words, there is only one class that can be non-trivial mod 2, can be non-trivial as an integer, but be trivial mod 2, and that's the top Smith class, which is non-zero. That this follows, for instance, by the argument that you just said about that Sergey said about, with the coboundary, right? So if you have, sorry, not the coboundary, the cup product. So 1 cup AI is AI plus 1.
This looks a little bit strange. 1 lives in dimension 0.
Yeah, no, this is not the argument. It's the
Maybe A1 cup.
A1, yes. Yes, sorry, A1, yes. A1 cup AI is A1 cup 2 times, let's say, B. This will be 2 times A1 cup B. And these are, since these are torsion elements, so these things, this will be 0, no? So there are different proofs of this, and another proof of the exact same argument I just gave. I mean, whenever you have this situation where you are 0 mod 2 and you are not 0, you can write a resolution when your term in the resolution is a cocycle. So then you stop there. So the next term of the resolution are actually 0. Because here we could write the term, so I have to make this go away. So the ith term is actually s times eta, and this is a cocycle. So if you follow the procedure of defining this resolution, the next terms would be 0. So this is another proof that whenever you have this non-zero integer class where it's 0 mod 2, after it, it has to be 0. And I think it also is related to the fact that the difference between the indices is at most 1. Mod 2 and non-mod 2. Okay, now if we do the computations and put this S eta and S eta prime, which is the corresponding one for the resolution, into the formula. Now, because these are top dimensional classes, and after that these chains are 0, and there is only a single term in the join, in the resolution of the top dimension, which is non-trivial. It has only one single term. And this single term turns out to be something like this, which is S eta times S eta prime times some coefficient. But this object, when you take the d of it, it is a 0 because it will go to 0. And so this is your term of the, this is actually I to I plus first term of the resolution of the join. And now you want to compute the cohomology class of D times this. Because it's odd dimensional, you want to compute the D times, cohomology of D times this, but when this S appears in both factors, D times that will be actually 0. And so this, the actual chain will be 0, which is, and therefore its cohomology class is also 0. And now this shows that whenever you have abstractions which are 0 modulo 2 in both K and L, and then in the join, so now we go into the original K and L. So then in the join complex of them, it actually, the abstraction to embeddability vanishes. And one thing is that now the complexes with this property also exist, and the complexes that Sergey introduced, I mean, they have, in his paper, they have one component abstraction which is 0 modulo 2, but it's non-trivial. And I actually computed by computer the abstraction for the dilated join of those complexes also has the same property. So therefore, those complexes actually work as examples where their join actually embeds in the double dimension, but they themselves, they don't embed. But I actually don't know how to directly prove that the mod 2 abstraction in the join is actually trivial and integer and it's also non-trivial. I have computed it, but I don't know how to prove it.
For the join, you mean the integer abstraction is 0, right?
Yes, for the join, the integer, and therefore the mod 2 abstraction is also 0, but the mod 2 abstraction in one lower level is actually non-trivial.
Well, I think I see how to do it geometrically. So you have two complexes, K and L. In K, you're able to divide your one-company abstraction by 2. And in L, you know that 2 times the one-company abstraction is 0. So both of these statements have a geometric meaning. So the one-company abstraction is a co-cycle which corresponds to the intersection of some top-dimensional simplexes, and so it lives on this product of two-dimensional simplexes, or if you prefer, on their join. So
yes, I agree that. So this last part is easy, but I don't know how to easily show that the abstraction in the join. I mean, what's the relation of the abstraction in the join to the abstraction in the factors? So that is
I'm trying to say this. Okay.
This formula.
Well, so you have this co-cycle, the one-company abstraction, which is it is possible to represent it just by the fundamental elementary co-cycle on some top-dimensional product of simplexes or join of simplexes. It has value 1 on this product. But also you can, if you move this embedding, this generic map, if you move it around, then because of this mapping cylinders, you will be able to divide it modulo 2. So you will run it into a situation where you have, instead of just one transversal intersection, you have 2 transversal intersections. It's possible to do it geometrically. So you have two elementary co-cycles sitting on 2 different pairs or products of simplexes. And this happens in like in one factor in K, and in L nothing happens. But then you just move this two elementary co-cycles, move them like they sit in just one factor, and you move them to another factor, like you rotate it in this product. And then in this other factor, because they appear in a different place in this other factor, it's just possible. So you combine them together and you obtain a double one-company abstraction for the other factor, and then it's 0. Well, I agree it's not completely clear, but this is an idea which maybe can be made accurate.
Yeah, and you're saying that idea for actually looking at the some map into R2D and another map and looking then in the join, right? Yes, I think that such a also yes, I agree that it should be possible to do it in terms of the trying to understand how these as you said, these intersections on these factors go into the interior of this joint, go inside. I mean, if we have them on different on the ends of this joint, and then how they correspond to the section. Yeah, yeah. I thought a little about that. I think there should be a geometric argument, as you said, in case of the embedding. I mean, for 2Z2, for the 2 case, P equals 2. But one reason I wrote it in this generality is because I wanted to have this theorem for general P, because I think this might have some applications in some other combinatorial problems when they look actually on ZP actions instead of Z2 and instead of actually embedding embeddings.
Well, so for other primes, you have the problem of removing p-fold intersection points. Yes. So there is a paper by Mabillard and Wagner about that. Yes.
Yeah, yes, I know that, but I'm not interested in embeddings then. I mean, I'm generally interested in how the Smith class of the join corresponds to the factors. And I can say now that, so if we have okay, I should say like this. So there is this, so this is the Smith index of K and a Smith index of L. And I also show with this I sub P. So let's now consider the general ZP action. And I sub P of K is the Smith index modulo P, and IP also is a Smith index modulo P. Now, if we have that these are actually equal, so this is I, and this is I sub P. If they're equal, then the index of K join L is the sum of the indices. So this is a nice stability situation. And now when both of them have one deficiency, which is the most that can be, then it is IPK plus 1, and which is IPL plus 1, then we have that the index of join, as we just showed, is goes one becomes one lower. So this is the situation I call unstable. And now if one of them is equal and the other one has this deficiency, then both of these can happen. And this actually depends on K. Doesn't depend on this L. So I think I have an example that so this is this Z2 complex. So this is this complex, which, so the two-dimensional Smith class of this is non-zero modulo 2. So this is a sphere, essentially, when you remove two pairs of antipodal points, and then you attach these handles. So one of them you attach, so these handles you attach in one side, in one hole with the degree 1, and the other one with degree -1. And now I have computed that, so this has some properties which doesn't allow to actually prove this stability. And this guy, if you, so let's K be this, then K join L, where L is actually has this property that index of L is, so top dimensional Smith class of it is non-zero, but is 0 modulo P. Then K join L actually has this property that index of K join L is, it actually drops it. It's index of K plus index of L -1. And but if we take for K, for instance, just a two-sphere it will be stable. So when we have one of these two complexes, non-trivial mode 2, another one trivial mode 2, but non-trivial as an integer, then both of the cases happen, and it depends more on the property of the complex, which is non-zero mode 2. Yeah.
Okay.
It doesn't depend on the vanishing. It depends on more interesting properties of the complex.
Okay, then it means that my idea was wrong. So then I don't understand your example. I have to think more about it.
So the property of this example is that there is a certificate, but this certificate of is not kind of equivalent. I mean, let's see. So there is a condition in my paper I've written as a condition C. That condition, is it satisfied, then we will have a stability in this situation. And for instance, it is satisfied when you have actually this K is a two-sphere. So if K is a two-sphere, then you will see that the cycle that we have, oh, I remember. So the condition is that the boundary of the certificate has to be equivariant. If your boundary is not equivariant, or if your boundary doesn't give you some nice thing to work with, actually, I think one can say if the boundary is equivariant. So if the boundary of your certificate for the Z2 yeah, so if you look at this antipodal sphere case, so this half disk, this is a certificate for the two-dimensional Smith class, I mean D class, D homology class. But you see that the boundary of this essentially covers all of your is S times something, and it contains what you need as a certificate for a lower dimensional class. But this complex doesn't have that property. This complex doesn't allow you to write the boundary of the certificate as it is 2 times something, but it's not S times something, S something. So the condition that K needs to satisfy is that, so the chain that certificates that the abstraction is 0, which has to have boundary of C has to be 0 mod 2 or mod P here. So let's say it has to be P times some X, right? So this means that it's 0 mod P. But the condition that I can use to show that it has to it works to be stable is that boundary of C has to be S times some Y. So if you have this condition, we can show stability, I mean, in K. If you have this condition in the certificate of the guy, which is actually non-trivial mod P. But if we have only that the boundary of our chain is a Px, but it is not S times X, then we cannot, I couldn't show it, and actually I found this example and I computed that the join of this example with the with other examples which are with this L, some example, some L actually gives you something whose 5-dimensional class is 0. Okay, so this is essentially all I wanted to say, and yeah, I also have a question that I think, because the people there are more, I mean, familiar with geometry and are more interested in geometry, I think maybe it's good to ask you.
Yeah, so what question?
Okay, so so are we finished with this? So we can, is there any question?
Any questions?
Okay, so let me say,
Coach, do you have a question?
Yes, I have two questions, but general, because of the introduction, I can ask my question later or now.
I think now is okay.
Yes, yeah. Please.
First question. So you started with simplices and collect some faces to dimension and prove then one component abstraction sometimes is vanished. So it means that you take symmetric group configuration of simplexes of the whole of the faces of the whole simplexes and do some calculation. And my question is, if you take the whole simplex with say some special group, for example cyclic group which permute the vertices, then you collect equivariant collection of faces. And this complex also interesting from point of view of endability comes from a very special group which sits into symmetric group, some very reduced configuration. Is it possible to do the calculation using your stuff, maybe with not with more delicate algebra inside, or nobody did it? And second question is,
I'm sorry. I did some mistake, Piotr Mikhailovich. It's my fault. But maybe we first discuss the first question, okay?
Yes.
Okay. Yes.
But
actually,
my question is not formal, but I think the direction is possible to collect more reducible symmetry, the more special symmetry configuration of the simplices and do just the same. Are there some paper on this direction, or nobody do it?
Actually, I'm not very familiar with that area, but what I suggested, I mean, the general approach of this is that whenever you have, I mean, two homology classes that you want to multiply together in some sense, and you want to show that this multiple is non-zero. So usually, I mean, most of the cohomology class, I mean, cohomology product theory doesn't work because this gives you relations. They don't give you, I mean, and all of these classes are zero divisors. So you cannot deduce that something is not zero or non-zero just by looking at the relations, right? But so this approach says that, okay, if you have some kind of a, instead of a cohomology object, so you have a chain that somehow certifies that your cohomology class is non-zero, and you have another chain that certifies the other cohomology class is zero. Now, if this combination of them is some kind of nice, then possibly there is some analogous combinations to the chains that will show that the product is non-zero. Yeah,
okay.
but I can say that there is this co-index theory, right? So which is in the paper of Conner Floyd. So I pretty much think that everything I said will work with the co-index theory. I mean, in that paper. I mean,
Piotr Mikhailovich,
it's generalization.
Is your question about non-abelian groups acting on complex, not ZP, not Z mod P, but some quaternion group, for example, yes?
Yes. Yes. Non-abelian, yes, it's interesting.
Yeah.
Some intermediate group between the whole symmetric group and some group non-abelian, yes. The problem of I see the top of the subject of the talk is quite another. You take just one skeleton, second skeleton, take a join and do the calculation of the join and something like this. And my question is not in this direction, because I am lost at the end of your talk. And at the beginning, you give more or less interesting example, and I try to understand better. But now I see that my question is not, is rather far from your results.
Yes, but I know that there are people who work also on analogs of, let's say, Boursuc-Ulam theorem, but when we have actions, I mean more general actions, perhaps symmetric group also, right? Yeah.
Yes, for example,
I'm not familiar with those.
Roman Kardashev and Dima Stepanov.
Yes.
So Roman Kardashev gave a talk about this in the fall in our seminar.
We have remember this talk, this very nice talk about economic applications. Better to repeat with other details. And,
but I suggest to look at my approach whenever you want to show that a product of two cohomology classes are non-zero.
Yes, okay. And then if you take not the top abstraction, but a little bottom, for example, I know that an arbitrary manifold of dimension n is embedded into n minus alpha 10, something like this. And it depends that all the Stiefel-Levitiny classes are, all the homology abstraction, primary abstraction are trivial, but this is not very strange. But in fact, the theorem is very, very complicated to prove that all the primary abstraction is sufficient in this special kind of dimension. And do you know that there is some idea to prove that this join you study embedded into a little lower dimension, top minus d, where d is small number, using just with this approach, or is it just very complicated?
So there is two things. So one is that whenever the index of the join drops by 1, then whenever it drops by 1 at most, right? And
yes, by 1, yes.
Yes, and so that's a different. And this theorems I say about the index, it doesn't depend on the dimension, right, of these complex. But when we want to deduce as you said, when we want to deduce embeddability, the dimension becomes important. And but I think for manifolds, so my main contribution here had been to work with integers, and I think it turns out that for manifolds we actually don't need integer coefficients, and we can do everything with mod 2, right? So and essentially the complexes, for instance, that Sergei constructed, they are non-manifolds, and so the embeddability for manifolds is decided already by Z2, and that is why in Besvina, Kopovich, Kleiner, they consider Z2 only. I mean, in a lot of other papers.
Thank you. Thank you very much for your answer.
You're welcome. You're welcome.
For your very interesting talk. For me, 3 hours is a long distance, but anyway, I was very happy to see you, to hear you. Thank you very much.
You're welcome. You're welcome. I'm happy to be here also. It's good that you liked it. Okay, so
other questions?
So I think there's some.
Thank you, Andrei. So I have a question. In your paper, I briefly looked at the introduction. I think you mentioned something about links and some.
About what?
About links, like links of vertices, and maybe
rings?
You want link, like.
Links. Okay.
Do you want to compute the one-company abstraction, global abstraction, using some local information from links? Is this what you meant there?
No, that was another paper. I mean, so that's a paper that says that if you have, so you can deduce something about links and intersections of the links from embeddability, right? So imagine you have some K. I mean, this is quite easy thing. So let's say this is 2 dimension in 4, right? And you take the 3 vertices and look at the intersections of these, link of these. Okay, so this will be graph, and it's easy to show that this graph has to be actually planar. And it's easier to show that it is linkless, but it is also planar because, I mean, this let's say this is L, then 3 join L actually lives in this space. So the embeddability of this triple intersection of joins in somehow 2 lower dimension, it follows from the embeddability of K, let's say, into 2D. So if we have D into 2D, then we can deduce something about these intersections. And for instance, with the result of this paper and also the previous results, so this triple intersection of links has 0 obstruction.
Okay, but does it relate in any way to your talk today?
Yes, because I first observed that, so that if L is linkless, if L is not a link, doesn't have a linkless embedding into the space, right? Then 3 join L cannot be embedded into R4. So that is quite easy. I mean, if you imagine it, and from that, I was interested in what happens to the join. So this was my start of the interest in this topic, because here we had 3 join L and 3 point set join L. Now it turns out that, as you also consider this problem in your paper, and this has a geometric solution, right? As you say, and but I wanted to extend it to the general K join L. I don't know still what applications I can make in that direction. So I used this observation to deduce that the number of simplices in in K2 when it's embeddable in R4 cannot be more than some function in the number of vertices. So because of these conditions, that has to be. And the planar graph has essentially a linear number of edges with respect to vertices. So you have these conditions on the intersections of the links, and this gives you a limit on this summation of these links, the size of the summation of size of these links. So the summation of size of these links is actually the number of, I think it's 3 times the number of, so the number of edges. So let's see, this shows the number of edges of link of V. So the summation of this, I think, is 3 times number of triangles. So therefore, if we have any kind of restrictions on how these intersections of these sets are limited, then we can obtain a bound on this number. So this was actually my first observation that I became interested in after this into now generalization of this. And I showed this 3 join L with some more complicated approach than one I already showed. But I realized that using dilated join actually helps a lot. But I want to say that it's actually possible to do everything in the dilated product.
And okay, and I have another question. So how about products of these complexes? So you constructed an example of 2 complexes which do not embed in the double dimension, but they are join embeds in the double dimension. And how about products? You don't have examples, it's open.
Exactly, so that was my question. So so this is called the generalized Menger conjecture. So let's have K. So this does not embed into, so this is of dimension D, does not embed into R to the 2D, and L of dimension, we can say the same D does not embed into R to the 2D. Now, what about K times L? So now I don't know, and actually I also don't have an intuition. I think that most probably this will not embed, but I think that what happens in join doesn't happen here. It's more, but I don't have any. So this is a guess. So, but I don't have any sign that actually this has to be true. But I think it will be very interesting to find some relation between, for example, the dilated join of this object and something about K join L. For instance, to the dilated product. So some relation between something, either dilated joiner or, but these 2 are now of the same dimension. So maybe one can find a map that helps, but I don't know actually here. I think it's a geometric question, and it has a different nature than the algebraic one.
Yeah, thank you. It's interesting.
You're welcome. You're welcome.
So you also had a question, right?
Yeah, that was this question. So I want to find a relation between either dilated join or dilated product of the product with either dilated join or dilated product of the join.
I don't know. I don't know about such relation. If it exists, then maybe it's not very simple.
I guess so too, but I think it's something that is not very direct. I mean, it's not that there's a nice, for instance, contraction that goes from one direction to the other. And I also want to ask the following question. Maybe you can say this, maybe you notice that, okay, so the complexes that have 0, so let's, this, so there is some K, as you showed, that this is 0, is not 0 as integer, but mod 2 of this is 0. Now, how can we show that the same situation is true also for the deleted join? So from this, deducing that possibly this is simple proof. So I haven't thought much, but I know that this has to be true. And for the complexes that you constructed, I actually computed this by computer, and this was true. But I don't have a proof that, I mean, this holds.
But there is something like equivariant homotopy equivalence between this deleted join and the suspension of the deleted product. Maybe not exactly equivariant homotopy equivalence, but it is up to some dimension. Yes, so there is an equivariant map in one direction, and
Yes.
it is highly connected. I think
the thing is that there is a map, but this map is not a. It's at some point there is a quotient, and that I think it's not homotopy equivalent.
yes, yes, but this map is highly connected, so it induces isomorphisms on cohomology in sufficiently high dimension.
Okay. Yes.
So you can just look at its homotopy fiber. If you like, so every map can be made into an inclusion by considering the mapping cylinder. Yes, and then to understand, so you want to understand the homomorphism on cohomology induced by this map. But then you can write the exact sequence of pair for the inclusion into the mapping cylinder. And you just need to compute the third term. And the third term, I think it is of low dimension. I think it's like dimension n, or maybe n+1 or n-1. But we have two n's, this deleted product and deleted join, they are like 2n. And that third term, well, it is probably high dimensional itself, but it collapses onto something small dimension. I mean, this mapping cone, it doesn't have topology in high dimensions. I think it is written in my paper.
Yes, I think so. And I think in the sequence of isomorphisms that I used to, or the sequence of arguments, equivalences I used to show that we can use this cohomology in deleted join as an abstraction. I use this existence of maps. But I think you're right. So because this contraction contracts something of lower dimension, then it doesn't change actually the higher dimension.
Yes. Yes, I think actually Arkady Skopinov had some argument like this in some paper like from 1990s or maybe early 2000s.
Yes, but the argument, yes, I wasn't noticed. Yeah, there is argument.
In my paper, I have a slightly different version of this argument, which is maybe easier to use because I just compute this third term and this cohomology of this mapping cone.
Which paper is that?
Well, it is this paper called One-Camping Abstraction and its Relatives. It is something there, I believe.
I see.
Okay. It is there. It's very easy, just less than half a page.
Yeah, I see it now, actually. It's quite easy. Yeah.
I know Skopinov paper about controllability of one-camping abstraction. Very nice paper. Then one-camping abstraction works when we do the approximation of singular map by embedding and singular map of polyhedra. I remember this nice paper by Arkady Borisovich.
Yes, so there is a whole theory about an extension of this embedding theory. If you are given a map, there is a question if it can be approximated by an embedding. And Arkady Skopinov actually found a version of uncommon abstraction which worked for that. And then uh, uh, you can also state it differently. If you have a, for example, you have a map into RK, and then you want to approximate it by an embedding in RK plus 1 or RK plus 2. Yes, so this seems to be a very interesting question. And you can try to extend your results in that direction too.
I see. Now that actually you said this, I mean, so the problem in general for Simplicial complexes, I mean, with embeddability into a lower than double dimension is that the abstractions, I mean, are not easily computable, right? And these are not chromological abstractions.
Maybe.
And but as the gentleman said here, I mean, for the manifolds, if indeed they are chromological abstractions for embedding into lower than double dimension, then perhaps a similar theory will work also there for showing that the join also embeds in lower dimension. But we just need a simple thing that yeah, essentially the mode 2 version of these arguments will be used. And I think the result then perhaps will not be that these things are non-embeddable. Then this will be a proof that whenever things are, sorry, the result will not be that something is embeddable. So I think it should be that whenever things are non-embeddable, then their join is also non-embeddable. Because there is everything is in Z2.
You mean manifolds?
In the manifold, yes. And a lower dimension, I mean lower than the double dimension. Yeah, another interesting question which is related is the Z index of the product. So if you have a Z, let's say a Z2 complex K and another Z2 complex L, then K times L, we can think of it as a Z2 complex by the action which is, let's say, T of K and T of L. So now it is true that the index, the ZP index, so let's, how do you show it? So let's say, so which means essentially the highest dimension, the lowest dimensional sphere that you can embed, that you can have a map from so your space to that. So let's say index of Z2 of K. So this is the Z2 index where is the lowest dimensional sphere, antipodal sphere that you can have an equivalent map from K to that space. Right? N, for instance. Because there is a map into the S infinity, so there is always some N. So you can always embed a complex into S infinity. Now the smallest dimension that you can actually embed into is called the Z2 index. Sorry, not embed, so any map. So sorry, any map that you can have an equivalent map. There is also, so this question is that because there is this equivalent maps into the K and L here, so index of the product is less than or equal to K and L. Now the question is that does the index actually drop? Are there complexes where the Z2 index is actually less than minimum of the two indexes?
I don't really know, but it's a pity that Chapin is not here today. He might know, or Volovyakov or Krashev. So there are people who better know such things than me.
Yes, yes, I think I know. Yeah, so this is, I mean, Roman Karasev, for instance, he works on this. This is a hard question, but there was a relation that they recently, I think, showed that if this index drops, then the index of K join L it also drops. So this was something I think they showed recently, and this relates to this what's called the Hedetnime conjecture also. But now what they actually showed that if this is true, the other thing is true, the other thing is true, but the index actually drops in even for with a suspension in general. But now what we just saw, what I showed in my paper, is that the index drops even if the homological abstractions here are non-trivial. I mean, if you have yeah. In general, the index drops even when you have a suspension of a general complex. So I think this index now we know. I think it drops when essentially the abstraction to this when the Z2 index is one less than the Smith index. So this is the where the homological abstraction is actually complete, and even in that situation, this index drops. But there are situations where the hard cases are the spaces where actually even the homology abstraction are all zero, but this index is large. This is not zero. Now, this happens when the original space is high dimensional compared to the, let's say, the Smith index. All right.
Yeah, sorry, I cannot say anything good here. Maybe I knew something, but I forgot.
No, I wanted to pose these questions. Maybe sometimes someone sees and has some ideas about it.
Well, so thank you very much for your talk. It was very interesting.
You're welcome.
I cannot say that I followed the calculations, and so I don't have a geometric argument for your theorem. So I will try to think a little bit about it. If I have some idea, I will let you know.
Yeah, I would be very happy. I mean, if you contact me and all of the audiences, I'm ready to answer questions, and yeah, I'll be happy to talk offline about everything.
All right, so thank you very much. Let's finish.
Okay, thank you.
Goodbye, everybody.
Goodbye.